You're listening to a podcast from 702 and Cape Talk.
702 and Cape Talk.
The Naked Scientist.
Chris, good morning.
Oh, good morning.
So this week is quite an interesting one. Japanese scientists announced this week that mice had been conceived using sperm flown in space. And not only that these mice are healthy and have normal fertility themselves. Why would we want to know that?
Well, the next big leap for humankind in space is to go to other planets, not just go to the moon, which is a relatively short journey, but possibly to Mars. And that's a long time in space. The shortest journey time is probably about 9 months. And one of the fundamental questions is, if we do go to another planet with a view to starting a human settlement or colony there, we need to know that we're not compromising our fertility along the way. In other words, will we be able to reproduce when we get there? Mm-hmm. And so the first step towards doing this is to ask, well, in relatively low orbits, when you just put sperm into space aboard the International Space Station, which is what this group did, is it adversely affected? And so there's a paper that's published this week in the journal PNAS. It's by researchers in Japan. It's Teruhiko Wakayama. He's a researcher at Yamanashi University, and they've done a lot of this kind of work. Mm-hmm. And what they did was to get sperm from mice, divide it into two samples. One set of those samples was freeze-dried at minus 95 degrees centigrade and sent to the International Space Station in 2013. It flew for 288 days in space and was then recovered to Earth. And it rejoined the other sample, which was freeze-dried in exactly the same way but kept on Earth. So they could directly compare the performance of these two sperm samples. Mm-hmm. They then fertilized mouse eggs that had not been into space with the sperm using a technique called ICSI, which is intracytoplasmic sperm injection. You basically inject the DNA from the sperm directly into the egg. They got mice back, which had the same number of offspring and the same numbers of males and females, showing that there hadn't been any obvious adverse effect on the sperm when they did this. And when those pups grew up, they themselves were healthy and they were fertile. They could have their own babies. And they did check the integrity of the DNA. They found there was a small amount of damage sustained by the sperm DNA in space, and that's because it's being impacted by 100 times more radiation in space than it would at the Earth's surface. But this is nonetheless quite reassuring that it looks like, at least in this low orbit, that when we're not exposed to huge amounts of radiation that you would get deeper in space, obviously, but at this low amount of Earth orbit, mammalian sperm, because this has never been done before, people have tried other animals' sperm, tested that, looks okay, but they've never done it with a mammal. It looks like actually this first step is encouraging.
So when we talk about these levels of cosmic radiation, and you say these are a little bit lower than what perhaps we might find further out, in terms of the difference between what we're exposed to on Earth and what these mice samples were exposed to in the International Space Station, I mean, what is the difference? What are we comparing here?
Well, when you're here on the Earth's surface, you have sitting above you more than 50 kilometres of atmosphere, and you also have the Earth's magnetosphere, which is the blanket of the magnetic field which is produced by the Earth. Mm-hmm. And these two elements have a very powerful effect of soaking up or diverting a lot of the cosmic radiation that comes in. Not all of it, but a decent proportion. And that protects us down here on the Earth's surface. When you're out in space, then the amount of that protection afforded to you is lower. The International Space Station's orbiting about 150 kilometres up, so it's still pretty close to the Earth, but it's still outside some of that protective blanketing. So the amount of radiation experienced by an astronaut and a sample aboard the ISS is about 100 times greater than you would get on the Earth's surface. So that's still nonetheless lower than you would encounter if you were aboard a probe going to Mars. And people know how much radiation you'd get on the way to Mars, because when they sent the Curiosity rover to Mars a few years back now, but that's the car-sized rover that's driving around on Mars at the moment looking for vestiges of life, for example, they actually had built into that rover a radiation detector, and they turned it on during the journey, and they found that the amount of radiation it received was the equivalent of an entire astronaut's lifetime operating dose, just in that journey that would be a route out to Mars and back. So there are high levels of radiation you can encounter out there, so we need to begin to address these sorts of questions.
Aha. 16 minutes after 10 o'clock, it is The Naked Scientist for this week. And of course, taking your questions, your science questions on any subject, as we try to understand some of the weird and wonderful parts of the world as well as the universe. And we take your calls on 021 446 0567, 011 883 0702. Whether you have a question about mice conceived using sperm flown in space and seemingly being healthy and able to have normal fertility themselves, and what that means for us as we try and figure out whether or not there can be life outside of Earth. Or if you have any other questions, we'd love to hear from you. You can also SMS us, of course, on 31702 and 31567.
702 and Cape Talk.
The Naked Scientist.
19 minutes after 10. Welcome back to the Sibis Makaza Show with me, Gugs Mhlungu, and the Naked Scientist, Chris Smith, talking about all things science and taking your calls and questions on 021 446 0567 and 011 883 0702. Chris, a question on 31702 about sex on Earth is easy because of gravity, but how would it work in space with zero gravity?
Okay, well, people have been looking not at mammalian sperm, but other animals' sperm and how that performs in space. And I know that the sperm mechanics are slightly different from human mechanics. I'll come to that in a second. But they did this more than 10 years ago with sperm from sea urchins. And I don't know why they chose sea urchins in the first instance, but they did. And the sperm appeared to be normal, and it appeared to have normal motility. So in other words, if you put the sperm into a liquid, it can still swim along. Now, in terms of people in space interacting, probably this would still be okay, because as long as you can actually arrive at the same point in time and space and get together, then potentially you could get the sperm where it needs to go and it would swim across the surface okay, because the way sperm actually swims, it's pushing with the beating of the tail on the sperm against the fluids on a surface, on the surface inside the woman, for example. And when you push something one way, you get a push in the opposite direction. So the sperm will effectively just push itself along and seems to have no problem swimming. So actually we think there shouldn't be a problem in that respect with the sperm A being motile, B the DNA integrity, and C the ability to swim. So it ought to be able to track down an egg like it normally does on Earth, despite the absence of gravity, because it's actually swimming through a fluid, and therefore it shouldn't be encumbered.
Someone asking the question on 31567. So we know that male mammals can produce or reproduce, certainly male mice, but what about women? So we've tested sperm in space, but not eggs.
Yeah, excellent question. Excellent question, even. And in fact, that is exactly what the Japanese group are going to do next. They started with the sperm because, A, it's a small sample. They can freeze dry it, and therefore it doesn't take up a lot of space. They don't have to send a freezer into space. And they do actually talk about this very question in their paper in PNAS this week. They say that this was a very compact way to do the initial phase of the experiment. Their next step is to send embryos. In other words, you fertilize an egg and send that up there, and then you can look at the integrity of a frozen embryo doing a similar experiment. So that's where they're going next.
We've got Bongani in Soweto with a question about radiation. Hello, Bongani.
Hi, Coach. How are you?
Very well, thank you.
Hi, Dr. Chris.
Hello.
Hi, how are you? I just want to have a question about radiation. It says that radiation is basically, it's like the penetrating electromagnetic radiation arising from radioactive decay of atomic nuclei. So all I want to know is when like a nuclear bomb like goes off, right? Like is gamma radiation like the most observed like force within radiation?
Okay, I think I get what you're asking. So if we have an explosion and we have nuclear fallout, what is that? Well, nuclear fallout's a range of things. When you have a nuclear bomb going off, it produces a series of nuclear products. These can include things that are emitters of gamma radiation. There are other forms of radiation. Though gamma radiation is light, but it's light with a very short wavelength, very high energy, so it goes into things and can damage things with a lot of electrons, like your DNA, so it can cause cancer. It's also very penetrating. It will go through meters of concrete. There are also other things that are produced in a atomic explosion, which include sources of beta radiation. Beta radiation are very fast-moving electrons, and they too can damage your DNA. And then there are other species that get made which produce alpha particles, which is the third type of ionizing radiation, alpha, beta, and gamma. And alpha decay is where the radioactive source emits the nucleus of a helium atom. So it's two protons and two neutrons stuck together, and they're positively charged. They're a big particle, relatively slow moving by comparison to the other things, but they can do damage close up. And if you inhale particles which are giving rise to that kind of radiation, these alpha particles, and they get into your body, if they're long-lived, then they can irradiate your tissues for a long time and damage you that way too. So there's a whole raft of ways in which you can be harmed by radioactive fallout. So the best thing is that we don't have radioactive fallout in the first place. And the way we don't have radioactive fallout is we don't have diplomatic fallout. So everyone needs to get on.
So Kim Jong-un and Trump need to remain amicable, not friends, but tolerate each other.
Needs to, exactly right. And China needs to exert its influence there too, because China is the biggest sort of funder and supporter of Korea, and so they will listen to China, and China needs to exert as much influence as it can.
We've got Sharma in Midrand. Hello, Sharma.
Hi, good morning. Good morning, Chris. Just to debate a bit, just a question on cold fusion. What is cold fusion, and can we generate electricity, and is it a cheaper option than any other electricity that we generate from coal or whatever? I'll listen on the radio.
Well, you might remember in the 1980s there was a huge fanfare because Pons and Fleischmann, who are two researchers in America, announced that they had achieved fusion at room temperature. And everyone said they were nuts. They produced evidence to suggest that they weren't nuts, and then everyone tried to repeat the experiment, and no one could. And that's why everyone said they were nuts. I think it's been disproven since. Now, fusion is where you take a nucleus and you push it into another atomic nucleus, and you go from two nuclei into one bigger nucleus. We know the physics of this very well because scientists have been studying it for a long time. It's what powers our sun. In the sun, which is a huge ball of hydrogen, you have enormous gravity, you have enormous amounts of temperature. It's very, very hot. And those two effects combine together in the centre of the sun, where the temperature is millions of degrees, to squeeze atoms together hard enough to make them fuse, and 4 atoms of hydrogen can fuse to make a helium nucleus, or a helium atom rather, which is the next element in the periodic table. And this process makes and slowly assembles bigger and bigger atoms. So we know fusion can happen, but just look at the environment in which it happens. You need millions of degrees. You need something thousands of times bigger than the Earth to have enough gravity to squeeze things hard enough. The prospects of being able to overcome the forces that keep atoms apart and keep the nuclei of atoms apart in a test tube at room temperature seems very, very unrealistic, which is why people were sceptical when people said they could achieve cold fusion. What scientists are trying to achieve here on Earth at the moment is fusion, because the way in which the physics of fusion would work means that unlike fission, which is how our present generation of nuclear power stations work, they split big heavy elements like uranium apart and make smaller elements, and in the process they release some energy. Fusion is taking very, very small, very, very light elements and merging them together. The products of a fission reaction will remain radioactive for hundreds of thousands of years. The products of a fusion reaction produce less radiation, and the products are radioactive for less long. So we regard this as a cleaner, safer, and more sustainable supply of energy, if we can get it to work. But at the moment, it's not producing sustained and reliable sources of energy. We're having to effectively put more energy in than we get out, but we're still trying to recreate on the Earth the conditions that exist on the sun by using, for instance, lasers and electromagnetic confinement in order to create a plasma that you can energize and cause to fuse. Scientists are working on it, but we're not there yet, and we're certainly not doing it at room temperature.
On 31702, Gugu in Randfontein asking the question, how long can astronauts be exposed to 100 times the radiation on Earth without side effects?
Well, it's not just the radiation. When you're in space, the environment of space is one for which we have not evolved to be in. You're in microgravity, which means all of the stimuli on your body to remain healthy are gone. Your bones very quickly begin to thin. You get osteoporosis, and people come back with the skeleton of someone who is in their 70s in some cases. Your muscles weaken because you're not doing load-bearing exercise in the same way. And these astronauts are exercising for 2 hours a day against big elastic bands, for example, because that sort of impact loading is the only thing that can sustain your muscles. And when people come back to Earth, they feel dreadfully weak. There are also consequences for people's eyesight. There is now a well-established phenomenon that the shape of the retina and the optic nerve in the back of the eye changes and flattens in people who spend considerable periods in space. And this is reflected when people do return to Earth in some cases, and in more than half of people, deterioration in their vision. We also have now seen experiments where people have exposed mice to the kinds of incident radiation you get in space, and it does damage the certain parts of the brain because you've got these very high energy particles whizzing through that seem to affect some parts of the brain, including the memory centres. So there are all kinds of consequences beyond just radiation. People have been up there and spent, say, a year in space, is the longest time spent there, and they return okay, but then we don't know what the long time would be like, and we also don't know what it would be like when you venture outside the protective envelope of being close to the Earth and try to do interplanetary space travel. We need to invent some kind of special shield to keep the radiation off people, because it's likely otherwise that they would be in a sorry state when they got to Mars or wherever we were going.
Kim on 31567 saying, does the moon follow a similar pattern across the seasons as the sun does, i.e. moving north in our winter and south in our summer, or does the moon remain over the Earth's equator, rise and set in the same plane all year round? That's from Kim on 31567.
Right, well, the moon is in orbit around the Earth, and it's not orbiting around the equator, its orbit's tilted a bit. So it's not doing a perfectly around the centre of the Earth type circle, but the Earth turns inside the moon. So the moon goes around the Earth, and it takes about 28 days to go from its starting point right the way around the Earth and back to where it started. But remember, of course, the Earth also turns inside the moon. So as the calendar goes forward, you see a slightly different view of the moon, and you see more or less of the moon, and you see it in a slightly different position of the sky each evening, relatively speaking, as it at the same time as it migrates its way across.
Thank you very much. That wraps up our conversation with the Naked Scientist for this week. Have yourself a fantastic weekend, Chris.
Thank you very much, and you, of course.